Welcome back to Physics 142. We've been talking about capacitors, these devices that store electric potential energy. And what I want to talk about in this video is what if we had not just one capacitor, but multiple capacitors? You might think, well, if I have several capacitors, maybe I could store more electric potential energy. And so we want to ask that question, is that true? What happens if I connect multiple capacitors together? Do I actually do a better job? And to think about that, it turns out there are two different ways that you can connect capacitors together. All right. One of the ways that you can connect capacitors, if we imagine drawing a circuit here that has a battery that's a source of electric potential, right? So we have the positive part and the minus part, right? You could imagine that the wire comes out here and is attached to a capacitor. And then we attach another capacitor and we put them in a row like that. And then this is our nice new circuit diagram. Now we have two capacitors in it, right? We'll call this capacitor capacitor C1, has an amount of capacitance, C1, and this capacitor here has an amount of capacitance, C2, all right? And so what we want to think about, this is called connecting the two capacitors in series, because one comes right after the other, right? That's in series. But it turns out there's another way we could connect them, right? So if we make our power supply again here, so here's our power supply, and you could imagine that I also could connect a capacitor to this power supply, right? So I connect a capacitor to the power supply, but then you could imagine, well, I could add another little wire here and put another capacitor next to it. All right, so now the wire splits, right? The wire splits, and you could have two capacitors next to each other, C1 and C2. All right, and with these two capacitors here, these capacitors, this is what we call connecting them in parallel. So this is connecting them in series, and this is in parallel. All right, so two capacitors in series, parallel. So two different ways of connecting them. And you might wonder, which is better, right? How do we want to do this? How do we figure out sort of what the total effective capacitance is of this circuit? Well, to think about that, we need to think about what happens here, all right? So let's think about this. So this power supply, you could imagine some positive charges flowing off of this power supply. The wire's just a conductor, there's no electric field there, so you just stay at this positive potential, flows along here, and you accumulate some charges plus Q on this plate of the capacitor. Well, if you get charges plus Q on this plate of the capacitor, that's going to push charges away down here, right? This bottom plate wants to respond, and that will give charge minus Q there, right? Because it for every charge you put here, it's going to push one away here. But all of those charges then are going to go and accumulate on this plate here, so you'll get plus Q again on this plate, which then will make this plate respond and give us minus Q right there, right? So, so what happens here is, whatever amount of charge we put on here ends up being the same as the amount of charge on here, right? So we can write that down in equation form. We can write that the total Q that comes off the battery is equal to the Q on capacitor 1, which is equal to the Q on capacitor 2. So all of those are the same, all right? However, if we think about the potential, well, up here we're at some high level of potential, right? But as we cross this capacitor, the potential changes, and as we cross another capacitor, the potential has to change more, right? That's the idea with capacitors, so that the total potential change going from down here, the source of potential, right? This low potential down here, high potential up here, right? Whatever that total potential difference is, well, that's going to be the potential across C1 plus the potential across C2. So we'll write that the total potential, right, the total potential difference across our battery, V, equals V1 plus V2. All right? So, well, now if we want to think about combining these and actually figuring out the amount of capacitance, we need to remember our formula for capacitance, right? And you might remember that our formula for capacitance was that C is equal to Q over V, where, we take the absolute value. We just take all these to be positive values, right? And so what we can do if we actually want to see the capacitance here is, well, if we want sort of the total capacitance of the circuit, I might maybe rearrange this formula a second so that I can substitute it in and say, well, V would be Q over C, right? So now I can go here and I could write, I could substitute in, I could say that the total Q divided by the total capacitance, right? I could plug that in here for V, right? And then I could plug in Q1 over over C1 for V1, right? And then I can plug in Q2 over C2 for V2, right? So this is just using this formula here and plugging in one in each of these spots for the potential. But now remember, all the Q's are the same, so those just cancel out. And so what we get is a formula that says that 1 over the total capacitance equals 1 over C1 plus 1 over C2. So when we add these together, the equivalent capacitance of the system, the total equivalent capacitance of the system, is actually not just adding the two capacitances together, but it's inverted. And so you could try plugging in some numbers. If you had, say, two capacitors that each had capacitance 2 farads or something like that, right? So you had 2 farads here and 2 farads here. You do 1 over 2, right? Plus 1 over 2, that would be a half plus a half, that's 1. 1 equals 1 over the capacitance, you invert that, it's just 1. The equivalent capacitance, if each of these was 2 farads, would actually just be 1 farad. So you actually get less total capacitance by combining them in series. All right, let's now think about how you might combine them in parallel. All right, here let's think about what happens is, well, you're going to get some charge Q that flows off here, right? Flows off, but some of the charge is going to go onto this one, and some of the charge is going to go on this one. So this one will have charge Q1, this one will have charge Q2, and they could potentially be different, right? Because it's just getting split, right? Some of it's going here, and some of it is going here. But what you might notice is that to go across this capacitor, like this top plate is at the same potential level as the top of the battery, right? It's all connected by a wire. There's no electric field there. So as long as you're just connected by a wire, you're always at the same potential. And this plate here, that's at a different potential, at the lower potential. So this battery has whatever delta V, whatever the V total across this is going to be equal to, right? V total here equals the V across this capacitor, which also must be the same as the V across this capacitor, because all the top plates, they're all at the same, they're just directly connected to the top of the potential, so that means they have that potential, and down here they're directly connected. So V equals V1 equals V2, right? If this had some V2, right, and V2 across it, a V1 across it, these are all the same. But the Q we said is different. What we do know is that if Q leaves, part of the Q goes into this one, part of the Q goes into that one. So Q total must be Q1 plus Q2. So now we know that, okay, so Q left the power supply and they all have the same potential across them. And we can combine these by using our capacitance equation to actually get to the capacitance, right? And here, what I want to do is I want to also write this formula as Q is C times V. And now I'm going to take this C times V expression and substitute it in for each of these Q's here. So I get that the total C times the total V equals C1 times V1 plus C2 times V2, where I'm just taking and plugging in Q equals C times V for here, right? These are C total times V total. This is C1 times V1, and this is C2 times V2. All right? But now remember, all the V's are the same, so the V's are going to cancel out. And so we get that the equivalent capacitance, when you combine them in parallel, is C1 plus C2. So if they're each 2 farads, you get 4 total farads, right? So the equivalent capacitance here adds as you might expect. And hopefully that makes some sense, because we realized that it just depends on the area and distance between these plates, right? So if I'm increasing the area by just sticking a bunch of plates together, then I would increase the capacitance. So when you combine them in parallel, your capacitance actually gets bigger. So 2 different ways of combining capacitors with surprisingly different results. In the next video, we'll do some practice with more complicated circuits and think about calculating the equivalent capacitance a little bit more.